All right, so if we look at this, you should have learned at some point that the electrons around a central atom need space. And because of that, they sort of act like balloons when you tie balloons together at where the closing is. And if you have two balloons to get as far away as possible from each other, they'll be in a line. So basically, they'll be like, like this. And they'll be 180 degrees away from each other. And if you put three balloons, it's sort of almost like this. They'll form sort of a triangle, trigonal planar. And if you have four balloons, then this balloon will start pushing that trigonal planar down and we'll have what's called a tetrahedral. And the angle between these is about 109 degrees there and 109 degrees there. It's actually a little less because lone pair electrons are closer to the atom than bonding pair. And because of that, they'll push these down a little bit more. So it's actually more like 107, I think. So it's a little less than 109. But anyway, the point of it is electrons repel each other. Electrons need space. And the best they can do in a three-dimensional area is, if you have four pair of electrons trying to avoid each other, is this tetrahedral shape. Now, the other thing you should have learned at some point is that the s orbital is sort of this spherical shape, and the p orbitals are what we call like a dumbbell shape. And these shapes come from high-end mathematics of probabilities where you'll find electrons based on, as I said, high-end mathematics that are much beyond anything I ever could understand. And when I took that course, just basically couldn't formulate a question and dropped it shortly thereafter. All right, so the p orbitals are on the x, y, and z axis. So they're 90 degrees to each other, and the s is just sort of there in the middle. So that makes it difficult for the electrons to get in this 109 degree area. So what happens is when carbon, which needs four electrons to become like a noble gas, wants to bond with four things, it can't really keep it in the 2s 2p situation that it has. That's not going to be very helpful for electrons to come in at a 90-degree angle. It wants those electrons to be spread out. So what carbon will do is it'll take its s orbital and its 3p orbitals and sort of dump them in a hybridizer. Sort of like if you watch Dora, she had that fix-it machine. Not dissimilar to that. In my mind, this doesn't really exist. But basically, you hybridize all these things. You kind of throw them in the blender, mix them all up, and then spit out four equal energy orbitals. And because they're equal energy, unlike where the S is of lower energy than the P, so that has to fill up first, these can all fill up equally. So you take this S and the 3P and you throw them in the hybridizer, and now you have four equivalent orbitals, each with one electron, and now something can come from each of these areas. You can situate these so they're all 109 degrees away from each other in a tetrahedral shape. You're not restricted anymore by the P being on 90 degrees from each other. Now you can just put them however you want, and however you want is 109-degree tetrahedral shape. And that is how that happens. So that is the sp3s because it takes one sp3 because it took three p orbitals. Now, if you have a situation like aluminum, which is everything neon is, plus 3s2, 3p1, this would kind of want to make three bonds. It's a long story about what's going on with aluminum there, but basically, if it wants to make three bonds, it has the same situation as carbon did. It has everything in the lower energy s. It doesn't have anything in one of the p's. It doesn't, to move an electron up and all that. So what it does instead is it takes the s and two of the p's, hybridizes them, mixes those up. So the two green here with the gray, mixes those up into three equal energy orbitals. And then it can put one electron in each of those. We call that sp2 because it took two p's and one s to make them. And since they're equal energy, they can now situate themselves in that trigonal planar shape that is more favorable so that each one is 180 degrees. Is that right? No. 60 degrees? 60 degrees from each other. 60. No, 360 divided by 3 is 120. There we are. 120 degree angles between all these. So there. So aluminum does that. If this were aluminum, this p orbital would be empty, and each of these would have one electron in it, and then like three things can come up, like chlorine could come up to each of those. Or carbon also does this. So when carbon forms a double bond with oxygen or something. It has 3 bonding areas around it, basically. It wants to be in this trigonal planar shape. And by doing this sp2 or hybridization, it will have these electrons situated like that. And you can imagine then that you have a hydrogen here and another hydrogen here, and then the oxygen, which will be, let's put it there, right? We'll do the same thing. We'll make a sp2 hybridization itself. So here's oxygen with its sp2. So it has 1 electron and then 2 that are bonded. So these would be the bond, the lone pair, and this will be the one up, and that'll be the one down for the carbon. And then the P, the empty P ones, which we can make blue. The empty P ones, which we can make blue. So oxygen will have it going up and down, and the carbon will have it going up and down. Each of these has an electron in it, and they'll sort of overlap and form that double bond. So this double bond here, which you can't even see anymore, is going to be that overlap of those P. All right, so that's sp2, and then sp orbitals is just 1 p with 1 s, and a situation like this could arise if you had basically, say, a carbon triple bonded with another carbon. So carbon, if you want to triple bond that with another carbon, you would want sp hybridization here, so it can be linear, right? So you're going to take an S and 1 P, make 2 equal orbitals that you can put equidistant away from each other, 180-degree angles. And then you would have, in this case, oh no, in this case, you would have, so a p orbital going up and down on each of these, and a p orbital, as you can see there, going out and back. So this one's coming out, and that one's going back, and this one's coming out, and that one's going back. And they'll overlap for the double bond and the triple bond. So that would be the same as basically 2 carbons, right? Single bonded with an sp, and then you have single bonds with hydrogens with the other sp, and then you would have double bonds and triple bonds in that overlapping p area. So another way to look at this is here where you have the p orbitals. They sort of overlap in a sideways way, whereas the head-on sp orbitals will be what we call a sigma bond, where they hit each other sort of head-on. All right, I don't know if that helped or not, but I think it did. And so the other thing, if you want to look at this, you can look at this web page here, which sort of does more of what I just showed you, how the carbon having 2 in the S and 2 in the P wants to formulate those into equal energy ones. And they try to draw some shapes just as ugly as mine were. All right, so I hope that helped. I will talk to you later.